We have an inverting op-amp configuration over here, and we have 6 questions. Let's start with some easy ones and slowly build our confidence in order to be able to attack something more challenging. I'll name this point x, and for the first question I'm asked to find how much is V out over V in if A is infinite, if the gain is infinite. Alright, let's not be confused over here, this is a voltage terminal, but I show this equivalently. They will probably try to confuse you with something like this. Don't worry about it. This is the same as showing the gain like this. Alright, it's the exact same thing. Now, this current is the same, right? It flows from here to here and then from here to here. It doesn't flow in the input. So this current is from Ohm's law, V in minus Vx over R in. The current flowing from here is Vx minus V out over Rf. Alright. Now I need to kick out Vx from my equation. I know this equation holds true for all op-amp configurations. Now in this equation I have between the output and the input voltages over here and the gain, I know that at the output I will get, because I have a negative feedback configuration, I know that I would have a finite output, a small output, I know it. But the gain is infinitely large, alright, it's infinite. Therefore, that means that V plus and V minus, the two input voltages over here, must be very, very close to each other. This difference must be very close to 0, alright? This means that, yeah, of course, V minus is Vx, alright? And therefore, that means that Vx must be 0. Since V plus is 0, V minus must be 0, and therefore Vx must be 0. Now, replacing 0 over here, I have that V out over V in, and then putting V in over here and Rf over here, is minus Rf over Rin. And this is a standard equation for the closed loop gain of the inverting op-amp configuration. How much is it? Well, I replaced the numbers, minus 100 kilo ohms over 1 kilo ohm, it's minus 100. Is X virtual ground? Yes, this point is a virtual ground. Why? Because the voltage here is 0. Alright, this voltage here is 0, but this does not short into the ground, so no current leaks into the ground over here. This is important, alright? Okay, we are done with the first one, and then we are asked to find how much is V out now if V in is a signal over here, like this, with 10 times the sign, alright? Which has some frequency over here, but our result does not really depend on the frequency. V out must be, alright, minus 100 times V out must be minus 100 times V in. So that means that I input my V in over here, multiply this, and I have 10 times 10 times 100, which is 10 times to the power of 3, times the sign, alright? This sign is the same as this sign. Because I'm lazy, I didn't write it over here. Alright. With this done over here, I am ready to advance into something more challenging. Now, I am given the gain again, but it's not infinite this time. It has some kind of value which is in decibels. Alright? Let's not panic over here and let's figure it out. Right, first of all, before I do anything, I will write my V out over V in again, just like before, but taking into account this new thing over here, that the gain is not infinite. Now I'll write the same equation as before, alright, for the current. This is the same current that's flowing in here and flowing over here. And again, I have this equation that holds true for the op-amp. Now, V minus is equal to Vx, alright? But we must pay close attention over here. This V plus, alright, is 0. This is 0. This A is finite. This A is finite. The gain is something, it has a value. The output, because it's an inverting op-amp configuration, is also finite. Right? This means that if the output is finite and the gain is finite, this means that this V minus also has to be finite, alright? It cannot be 0 like before, because if it was 0, it would mean that this whole term would be 0 and the output would be a 0 value, alright? Now, that means that I don't panic, I just go ahead, replace V minus with Vx, and then divide both terms with a and with a minus, and I have that Vx is minus V out over a. Very simply. And now I'm ready to eliminate Vx from the above equation. Alright? This was a difficult thing over here. We must remember this. We must remember that this does not mean that it is 0 always. This holds only true. This thing is only 0 when the gain is infinite. When it isn't, it is something like this. And of course you can see that if the a was infinite, Vx would be getting close to 0, alright, from this equation. Now, going ahead and replacing this with this, and doing some math over here, don't worry about it a lot. You can go ahead and practice it. You can write me down in the comments how you did it. So I leave this up to you, and we have an output over the input. I have a f over r in on my p out over v in equation, but I also have the gain over here. If the gain was infinite, like before, this whole term would be 0, and I would have r minus rf over r in, as I had previously, alright? This is a corrective term now. Now, I'm given that the gain is 20 decibels, right? This means that I can write it like this. This means that the gain is 10 to the power of 20 over 20. Alright, this means this holds true for decibels. If I had an input of 30 decibels, a gain of 30 decibels, the gain here would be 10 times to the 30 over 20. Alright, that would be confused. Which gives me a gain of 10 over here, quite small. I go ahead and replace everything here. This over this gives me 100, this over this gives me 100 plus 1, 101 over 10. With a minus in front, I do the math, and V out over V in must be equal to minus 9.01. So this is my gain now. Is X a virtual ground? No, X is not a virtual ground because the voltage here is not 0. It has a finite value of V out over A, alright, with a minus in front. So we must be careful. This is some trivial questions that maybe you will be asked in a quiz manner, alright, or an exercise. So this is done, and let's go to the next one. The next one asks us how much is V out if V in has this value. So again, I go ahead and replace this thing over here in my previous equation, alright. V out is minus 9.01 times this, so it's this thing over here, alright, the same sign. Again, the frequency doesn't really bother me, alright, doesn't do anything. The output over the input does not depend on the frequency. So this is done. Now let's go into some more advanced territory. If the op-amp is not ideal, it can have a corner frequency, as we call it, or a cutoff frequency, or whatever. This is an eternal frequency of the op-amp. From the point onwards, the gain starts to fall. This means that when we reach the 1 MHz frequency at the input, this op-amp over here is going to start to lose gain. Alright, it's going to start to lose gain. It's going to have a slew rate, as you probably have seen it already. But we're not going to worry about slew rate for now. It's not the point of this exercise. Right, so what does this mean for my equations? Very simply and very easily. I go first of all and transform my frequency to angular speed. So the frequency is equal to the angular speed over 2 pi. Of course, this is an absolute value, right? This is a complex number, all right? But don't worry about it. It's an angular speed, essentially r over s, which means it will be 10 to the power of 6. And I go ahead and replace, this is the pole as we call it, all right? That's why I have a p over here, sp. So sp is equal, I could also write this, by the way, as j omega, all right? This is the absolute value, is the same as the absolute value of the j omega. All right, I go ahead and replace the gain wherever I had it with the gain over 1 plus s over sp. All right, this is the pole over here. So I go to my previous equation over here and I go ahead and replace the gain over down here with this value. All right, this thing. Now I will go ahead and replace all the values over here just so I can make my life easier and find the result much faster. So I go ahead and replace everything, all right, as I know it. Now, what I'm going to do is, I'm going to do some math over here, all right. I multiply this with this, and then I divide this with this. And then I go ahead, do a little bit of more math, and then I reduce my equation to something useful, which is an expression like this, which means that I have something at the denominator over 1 plus the frequency, all right, or the speed, over some value over here, which is the new pole of this whole configuration. So we see that this thing, this op-amp had a frequency response of something which had a pole over at 2 pi 10 to the power of 6, but the whole thing like this has a pole somewhere else at the 1.1 times this frequency, all right? Now, this means that Vout over Vin is this, so we are done with this. Now, it is clear that the output over the input depends on the frequency. So, we must be careful now. What if the input now is 10 times this signal, the same as previously, all right? I want us to find if this thing passes unscathed at the output. Unscathed means that it doesn't change form, let's say. So it doesn't become something strange. So it must be recognizable as a sine. So as a sine with the same frequency, etc. Now, I go to my previous equation. I replace the frequency with 2 pi 10 to the times 3. All right, this is the angular speed over here. I replace my angular speed in the frequency. Okay, this obviously this is an absolute value. And I have that Vout over Vin, if I do the math, must be equal to this value over here. Why? Well, this 10 to the power of 3 number over here, all right, if I had over here, it's much smaller than this 10 to the power of 3. This whole thing would be very close to 0, all right, 10 to the power of minus 3. So this is relatively close to 0 because I add it with 1. All right, so this whole thing is about 10 to the power of minus 3, which is about 0 in relation to this 1 over here. All right, this is very small in relation to this. So it's like we have nothing over here. So this means that the out over V in is minus 99.01. Alright. If this confuses you, I get it. But as engineers, we must be comfortable with making these simplifications whenever we have to, in order to simplify our lives. Now the out will be equal to 90.1 sine. Alright? Why? Because I found the frequency response over here. I multiply the outputs, this gain with the output, is the same thing as we had before, all right? It's like we don't have this dominant pole over here. It's like we don't have anything, all right? Why? Because the frequency is very small in relation to this frequency. So the signal passes unscathed at the output, alright, I have a signal at the output, as I expect, so everything seems fine. Now, how about when the input is the same signal, but the frequency is much higher over here, as you see? Well, I will pull a trick on you, and I will write this expression like this, just multiply this thing with the numerator and the denominator. And now I did this for something that will be very clear now. Well, if the frequency is 10 times to the power of 9, all right, now this term is much higher than this term over here, all right? That means that this term overwhelms this term. So that means that I can comfortably say that this thing is 0, all right? This thing is 0 in relation to this always. So that means that I can go ahead and do the math over here, and I'm going to have in the denominator 10 to the power of 9. I have in the denominator 10 to the power of 6 times 10 to the power of 7. So this whole thing would be about 10 times to the minus 100. All right? All right. All right. Ten times to the minus 100. Minus 100. That means that this gain downscales the input by 100 times. All right. Now we see how detrimental is this corner frequency inside this op-amp, this cutoff frequency. So the gain is 100 times lower. The output is 100 times lower than the input. So that means that the output is 0. All right. This is 0. Because it's so small, we say that it is 0. First of all, when the output over the input starts becoming lower than 1, this thing no longer amplifies. So this doesn't work as an amplification. It doesn't work as an amplifier anymore. And when it gets 100 times lower, well, this thing's practically 0. So we said that the output is 0. Again, if you have an issue with this, I get it. But normally output doesn't really pass, all right? This works as a low pass filter in small frequencies, all right? The output must be 0 because the gain is so small, the output is so small, practically is 0. So the output signal is not unscathed, the input signal is not unscathed, the output is, all right, is 0. So this input signal doesn't pass over here. And we are done with this too. Now we have seen two cases where this frequency is much smaller than this 1 MHz, and one case where this frequency is much higher. But what if this frequency is close to this, right? What if I cannot simplify these equations over here, like I did here, like I did here? Well, in that case, this thing will work as something resembling an op-amp integrator, all right? I have an op-amp integrator video in this channel, so you can check it out later if you want. But Essentially, that means that this will have a very strange behavior. Alright, that was it for today. Check out the op-amp playlist over here, check out the op-amp integrator, and see you around. Study well and take care.